Yes, welcome back. Hello, everyone. This is the lecture on um, deep learning. So, as we covered in the first lecture, mm, um, uh, the neural network I just presented, the multi-layer perceptron, sort of was invented, I think it was 86, and then I would say it was quite popular until the end of the 90s. But then people got, the performance was good, but people, yeah, didn't like it that there was not a good, clean mathematical theory behind it, and um, also it looked more like a heuristics than a science. And then uh, what people consider now a neural network winter happened. So maybe from the late 1990s until maybe 2011, 2010, 2011. And during that time, more theoretically founded approaches were popular, like kernel approaches, support vector machine, Bayesian networks, graphical models. But yeah, it became maybe, neural networks or machine learning became a very popular area in vision and other areas. So it had a lot of other areas which used which used machine learning. So that was great, but it was sort of running out of steam a little bit. Became very theoretical and uh, experimentally. Not too much was happening. Um, uh, and around 2010, um, neural networks again became extremely popular. And the three critical names here are Geoffrey Hinton, Jan LeCun, and Yoshua Bengio. And Jan LeCun is New York University and Facebook AI Lab in New York, and I think also Paris. Yoshua Bengio is with the University of Montreal. And they are two world-class researchers, extremely bright people who never stop working on neural networks, even when it was completely unpopular. So definitely was not because they didn't have the skills to do other things. And Geoffrey Hinton, he's the co-inventor of the multi-layer perceptron, Boltzmann machines, and other things. He is with the University of Toronto since a few years, and also has some occupation with Google. Um, and he says it started in 2006, fast learning algorithm for deep belief nets. But initially it was not recognized to be very important, because initially the performance was good, or maybe even very good, but there was not enough that people really um, thought we all have to do deep learning now. And it was really the excellent performance on benchmark problems, which made everybody pay attention. In Europe, one person who was also holding out with neural networks was Jürgen Schmidhuber, originally TUM Munich, and now he's a co-leader of AI lab in Switzerland, ITSIA. And the real breakthrough was really the performance, not because people suddenly loved neural networks. So these are the three people I mentioned. Schmidhuber calls them the deep learning conspiracy. They won the Turing Award, and I think they definitely also deserved it. So Geoff Hinton, who really got the interest in deep learning started, and Yann LeCun, who um, was the inventor of the convolutional neural networks, or ConvNets, and Yoshua Benjo from the University of Montreal, and all of them are still very active and contributing a lot to the field. This is Jürgen Schmidhuber, who thinks he should get more credit for some of the innovations. Maybe you followed the discussions, which are a little bit nasty, and maybe you can form your own opinion at some point. Yeah, this is another important figure, Kai Yu. He's a former student, PhD student in my team, and he then went to NEC Labs, then to Baidu, and now a couple of years ago he formed his own company, Horizon Robotics, which is valued at a couple billion dollars, so it's quite successful. One thing they're doing, they are developing special chips where deep neural networks can be calculated very efficiently with low energy consumption. Yeah, what belongs to deep learning? Of course, it's a quickly evolving field. In general, so the first approach might be to say it's a multi-layer perceptron, so a neural network with many and large hidden layers. So we don't only have one hidden layer, like in the talked about in the lecture on neural networks, but there are many layers and they are quite large. Then convolutional neural networks, which are very powerful in image analysis. Deep reinforcement learning, which I might cover in a different lecture, where you have these great successes in learning how to play games by this technology, and the big successes of Google DeepMind, who are more or less champions of every board game there is. Then representation learning is a strong idea because you attach vectors to discrete entities like words, entities, predicates, samples, and in this way make it accessible to continuous computations. And then there are deep generative models, for example, the variational autoencoder and the GANs, which we will cover in this lecture. So here are some examples of the successes. So I like this definition. AI is about creating machines that perform functions that require intelligence when performed by people. So that covers, it might not be a very precise definition, but it covers a lot. So we talked about games, successes in Go, AlphaZero. Translations, each time you use Google Translate, you're using deep learning neural network. Question answering systems. IBM Watson was a certain breakthrough there. Face recognition, autonomous driving, speech recognition, all of them in the smartphones are now using deep learning, drones and robots, and maybe more to come. Yeah, I think I mentioned the main technologies. So there's convolutional deep learning is mostly applied to images, recurrent deep learning to sequential data, like translation and speech recognition, reinforcement deep learning for the optimization of games, and generative adversarial networks, or GANs, for these amazing image transformations people are doing. And also students can do amazing things. So this is a game. I spy with my little eye, or I see something you don't see, and The goal is by a dialogue system to find out what the oracle, what object in the image the oracle is thinking about. So I don't want to go into the details, but it uses text models, so LSTM, which is a recurrent neural network. It uses image analysis, convolutional deep learning, and it uses reinforcement learning for for the optimization of the whole thing. So it's really a lot about talents and the way people interact these days with a lot of exchange of papers, of code. So it's a very fast-moving field, and if you want to stay in this field, you have to keep up with the literature. But it's not too difficult because so the important thing typically propagates, and you sort of filter out what is important, what is not important. And this is definitely happening much more than it was happening in the years before. So here are some reasons why deep learning works so well. So it's more labeled data. So the data sets for training simply got larger and more meaningful. And labeling often is a manual effort, so it's costs something. But companies are investing in labeling data, and some of that becomes publicly available for everybody to use. Then, as I said, deeper models, so more layers and deeper neural networks, but also new algorithms. So it's not just more and more computational power, it's also really smart algorithms and new applications. End-to-end training, which means that you're really optimizing for the task you're interesting to solve, and not for some intermediate things which might lead to more modular solutions, but the performance is typically better if you do end-to-end training. Then the computational power, so GPU computing is used a lot in deep learning, so there's a lot of that. And as I said, the community, which is just very active, exchanging ideas, making code available. So it's a quickly evolving field. And students can become really advanced more or less just by themselves or by talking to peers, to other students. Yeah, it's pretty amazing. Of course, deep learning also needs a lot of data, or as I call it here, deep knowledge, facts and models. So for question answering, huge document repositories. For IBM Watson, for example, for autonomous driving, you need detailed maps and positioning systems. In industry, we're talking about IoT, so Internet of Things and big data. In healthcare, it's about detailed patient profiles. So you want to know a lot about a patient, but also have a lot of data to train on. There's web content and Wikipedia for humans, and knowledge graphs for machines. So knowledge graphs is something we might talk about later. Not so much focus of this lecture. So this was 2013, and the answers are more or less still correct. What are the reasons for the success of deep learning? What is the deep learning recipe? So first thing is take a large data set. And that's definitely true if you have to train for a new task on scratch. But people work a lot with pre-trained models where they only adapt they take a deep neural network where somebody spent a lot of time and effort to optimize it, and then simply maybe remove the last layer and adapt it very quickly for new tasks. But if you want to train a neural network for a new domain, you have to have a really large data set. Then take a neural network with many large layers. So here's some numbers, 7 maybe. So sometimes people do 3, sometimes 7, sometimes hundreds, and many nodes per layer, so neurons per layer, so maybe 1,000. Optionally use GPU computing, so graphical processing units, the one which is also accelerating your games. And they're more or less the ones which are used in gaming. But there, of course, there are also some special developments. And that's particularly important if you use images and convolutional neural networks, for example. Then train with stochastic gradient descent. So we already know about stochastic gradient descent. And this is also used in deep learning, so you don't have to learn about fancy optimization methods necessarily. Except for the output layer, use rectified linear units. So that's a particular transfer function of a neural network. So it's either, so if the input h or the activation h is negative, the output is 0. If it's positive, it's just h, so it's linear. And that speeds up learning quite drastically. Regularize with dropout, so it's a new regularization method. Sometimes optionally initialize weights with unsupervised learning. So that was used initially very much. Then it fell out of favor, and now people are talking about this again because a lot of the amazing capabilities of humans, of children, cannot be explained simply by supervised learning. And if the input is spatial, for example, a picture, an image, use convolutional networks with weight sharing and max pooling. So a deep neural network learns complex application-specific features trained on many data points, so it can deal with a large N. And of course, it comes with stochastic gradient descent, that you have this sort of online type of learning capability where the number of data is not a critical point. If you have much data, you just do fewer epochs. If you have fewer data, you use more epochs. So that's not trivial, but it's easy to explain. Data are given in some feature space or some input space, and this can be raw pixel images. So you don't need any additional feature engineering or basis function design, as we discussed before. You can choose, in the lecture on fixed basis function, we talked about polynomials or Gaussian basis functions or some application-specific basis functions. So this feature engineering is sometimes called is not necessary. You can work on the raw pixel data. And that also means that you don't have to have an amazing amount of domain knowledge, because if you just train on the raw data, you don't need to know about important features in your data. And you can also work with large input dimensions, so large N and large M. And it requires, it's efficient, so it requires fewer resources in a hierarchical layered structure. And it has something which is termed compositionality. So this means that the neural network, but also the target function, has this ability, or let's consider first the neural network. So essentially you're calculating a function of a function of a function in these deep architectures, and this can be considered a hierarchical processing of information, and it's something which seems to match a lot of target target functions which occur in the real world. We come to this later. So let's start with a large data set. So when decision boundaries are complex, you need a lot of data to describe the details of those boundaries, so that's why you need a lot of data. And a complex multi-layer neural network or deep learning is able to capture, to exploit these details which are supplied by a large data set. So what is a large data set? So here's a statement from 2016. A rough rule of thumb is that a supervised deep learning algorithm will generally achieve acceptable performance with around 5,000 labeled examples per category. So if you have 10 categories, you need 50,000 labeled examples. And it will match or exceed human performance when trained with a data set containing at least 10 million labeled examples. So the statement is from Goodfellow from Deep Learning. And this, again, is the situation where you have to train from scratch, where you have to train everything. But in many applications, you can use pre-trained networks, so these numbers are much lower in this case. It has been possible to train small to medium-sized problems since the early 1990s. So the point here is you need large networks. And in deep learning, people use large neural networks, so maybe 10 layers with 1,000 neurons per layer. And sometimes they go to the extreme. So ResNet from 2015 had 152 layers. So that's not typical, but ResNet is one of the popular neural networks. So it is used, and not just by the people who invented it, but also by other people. You need graphical processing units because they are very effective in doing matrix vector calculations very efficiently. And it has been shown to speed up training algorithms by orders of magnitudes. And the interesting thing is that the parallel computing was considered sort of a nightmare. Students spent their whole PhD on implementing some algorithm, and then it was not much faster than the non-parallel algorithm. It gave you a lot of headache, a lot of problems, but in these problems and with GPUs, it's often just a matter of setting a particular flag when you call a function. So it's really simple to use. So the highly parallel structure makes them more efficient than general purpose CPUs for algorithms where processing of large blocks of data is done in parallel. So it's really used a lot, GPU computing. Not, I wouldn't say always, but in particular, if you have something like images as your input, you definitely use GPU computing. Yeah, there's something called general purpose computing on graphics processing units, or GPU. So they are so they're trying to make computer graphics GPUs more general, but to my understanding is that a lot of people just use standard GPUs, which might be in your laptop. But of course, then you want to use several of them, and then you need several cores. So it becomes a little bit more expensive. But it's not hugely expensive. No? So stochastic gradient descent, we already learned about. When the gradient is calculated on a single training pattern or a mini batch SGD, where you maybe use a few data points, a mini batch of data points to calculate the gradient. One trick people are using is gradient clipping. So if the magnitude of your gradient becomes larger than threshold, then you clip it to that threshold. So you don't let the gradients become too large. In lecture on neural networks, we discussed about the problem of local optima, but the general wisdom is that they are don't appear to be a major problem. The current thinking is that there are many local optima, but they're all very good. So it doesn't matter which one your system finds. And that's still one of the riddles. And at the end of the lecture, I will discuss it a little bit more. That why is this so? It's not like there's no local optima at all, but it's not a very large danger that you find one of them and you don't come out of them. So the general perception is that deep learning doesn't really suffer from the problem of local optima. Then, as I discussed before, as we discussed before in the lecture of deep learning or neural networks, tuning the learning parameter can be tricky. If it's too small, it takes forever. If it's too large, learning can become unstable. So people found solutions to this problem. So the learning rate is adaptively altered. So typically you want to start maybe with a large learning rate, and then you want to go down when your learning has already trying to learn the finer details of your problem. So here's the Adagrad version, which means the new WJ is the old WJ minus learning rate times gradient J, but then you divide it by the square root of this big G JJ, and this GJJ is an average or sum over the square of the gradients, either from beginning of training or in a time window. So if this square of the gradients is very large, then the learning rate will be tuned down to guarantee stability. If the sum of the squared gradients is small, then learning rate becomes larger. So yeah, extreme parameter updates get dampened, while parameters which get fewer small updates receive higher learning rates. The what is now very popular is Adam. So if you want to use adaptive learning rates, maybe the first choice would be Adam. That's what the students are using, for example. Also, in the output layer typically is a sigmoidal layer or a softmax layer, but the internal neurons might have this might be rectified linear functions, also called ReLUs. So it's, as I said before, the maximum of 0 or h. So h is the weighted input, and so if if h is negative, it's 0. If it's positive, then it's h. And this can turn neurons off if the activation is 0, or it simply becomes a linear neuron if h is larger than 0. And this has, for example, a great big effect in backpropagation learning, that the gradient stays at it doesn't vanish. So there's this vanishing gradient problem, which means if you do backpropagation through many layers, the gradient becomes smaller and smaller, and the adaptation becomes very slow. But if you don't have these squashing functions, the sigmoidal transfer, then the gradient becomes stays sizable, and backpropagation works quite well. ReLU is considered maybe heuristics, but it can also derive from from the following way. You sum up all the responses of identical neurons, same inputs and output weights, where only the threshold bias is varying, and this then becomes similar to a rectified linear neuron. Yeah, it reduces the effect of the vanishing gradient, which we have discussed already. It seems a little strange because the neurons which become zero, have a zero output, becomes insensitive to the error, but a sufficient number of neurons stay alive. And of course, it's which one turn off and on depend on age. So it's not that a neuron is always off. As soon as the age, the weighted input becomes larger than zero, it turns on. But the output is for classification tasks, says the sigmoidal layer, and for multi-class, you typically use the cross-entropy cost function. No, sorry, for the sigmoidal, you use the cross-entropy cost function, and for softmax, use the softmax cost function. So here are examples. So this is a linear transfer function. This is a perceptron. It goes from -1 to 1. This is a sigmoidal transfer function. So transfer function, linear transfer function, perception transfer function, sigmoidal transfer function. That's the one used in neural networks. Sometimes people, in particular in the hidden units, don't use the sigmoid but the tanh, which is exactly sigmoid, but it goes from -1 to 1 and has this property that for small h's it has a linear behavior, and that's sometimes useful in applications. And then the rectified linear unit, which we discussed, it's 0 for negative h and then increases linearly with h. Then another innovation is dropout regularization, which is an interesting idea. Maybe something you would not think of yourself. So for each training instance, so for each pattern, you first remove 50% of all hidden units, randomly chosen, and only do the error calculation and the adaptation on the remaining networks. And this is stochastic, so for each pattern, you might switch off another 50% of all hidden units. For testing, so when you, after training and for prediction, use all hidden units but multiply all outgoing weights by 1/2 to compensate that now you have a complete neural network. So it's like a committee machine where each, that's again, people like with dropout, people try to find an explanation why it works. So the explanation is that it's like a committee machine where each architecture is a committee member, but the committee members share weights. And it has something to do with calculating the geometric mean, which is the average of the log of the predictions, and then taking the exponent afterwards. So this is sort of an attempt to explain why dropout works so well. It works better than stop training. You don't need a stopping rule, so you can train forever. And there's some variations. Some people do even drop out in the input layer. There's different committee members in this interpretation would see different inputs. So Hinton's recommendation in 2000, when was it, 13 or 16, use a large enough neural network so that it overfits on your data and then regularize using dropout. And Goodfellow, who is one of the innovative guys in deep learning, dropout provides an inexpensive approximation to training and evaluating a backed ensemble of exponentially many neural networks. So that's a way of explaining it, but not of what you're doing. What you're doing is what I described. There's also a variant called drop connect, which is drop out of single connection, not of a whole neuron. Then people use weight regularization. So weight decay works and it's sometimes used, but weight regularization often works even better. So for each neuron, you normalize the incoming weight vector to have the same maximum length. That's if the incoming weight vector, the magnitude is larger than alpha, you divide it by the length of the vector magnitude. And so the incoming weights have a maximum weight vector, and backpropagation is performed through the normalization. So this is another interesting regularization approach people are using. Then there's something called batch normalization, which is maybe slightly more difficult to understand. So let Zj be the output of a neuron after applying the nonlinear transfer function. Then each neuron Zj is normalized separately as so we get this Z tilde j, which is Zj, so the output minus the mean vector divided by the square root of the variance plus epsilon. And the mean and the variance are calculated specifically for that neuron over a small batch, so over a small size of data points. Also backpropagation again is performed through these operations, and epsilon is a small number to ensure stability. So batch normalization is quite popular and can greatly improve the training of deep networks. And the explanation is that the mean and the variance of a neuron's output after the normalization don't change. Typically, it's applied after the application of the ReNU, but it can also be applied before the nonlinearity. Layer normalization is a variant which also works well in the recurrent neural networks. So this is the principle of operation. So we have the output of the ReNU. Then you do this normalization, which gives you this Z tilde, and then you apply the output weights to get the input to the next ReNU layer. So the normalization is like neuron by neuron. Well, this is maybe an architecture, a typical architecture. So you have inputs, in this case 3 inputs. Then you have a hidden layer, then you normalize the outputs. Then you have the weights, then you have a hidden layer again, you normalize the outputs. You have a hidden layer again, you normalize the outputs, and then you calculate your outputs. So since the neural networks are so large, and for such a large and deep neural network, maybe you still have only a small, comparably small number of training data. And in particular, you have maybe a small number of labeled data, but maybe a lot of unlabeled data. So maybe if somebody gives you a lot of images, but only a small number of them, relatively small number, it is labeled if it's a cat on the image or not. But maybe you can use all the images also to sort of pre-structure your neural network in a smart way. So one approach is the first layer is initialized with the encoder part of an autoencoder. We will discuss autoencoders in a separate lecture. Or several layers are initialized by a stacked autoencoder, again discussed in another lecture. Or initially, when deep learning started, people used the restricted Boltzmann machine or deep Boltzmann machine and deep belief networks. But this is not that much used anymore. And the wisdom is that if you have enough labeled data, this initialization with unsupervised learning doesn't give you anything. But the challenge of using a lot of unsupervised data in your learning, that's still a research challenge even today. So in the this is multitask learning. So let me just explain it. So you have inputs, you have a lot of hidden layers, and then you have different tasks. So maybe you originally trained your deep neural network for task number one, and you have a lot of data for that task, and you're really optimizing your neural network to be good at task number one. And then but you also want to solve task number two and task number three. So you take most of the layers of your first neural network where you had maybe a lot of data to train, and only retrain the last layer, sometimes even not even the hidden layer anymore, just the connection from the last hidden to the output layer. Um, and then you can sort of transfer the information you have learned before to the new task 2 and task 3. That's how these things are typically used, or you have a lot of data for the 3 tasks, and you still decide to train one neural network with a lot of shared layers to also maybe get a better network, or to improve the performance in general. So this is often used if you don't have enough data or enough resources or enough patience to really train a complete deep neural network. So you take one which already exists, so maybe train for another imaging task, and just replace the last layer, and that works surprisingly well. And there are, of course, a lot of variations on this basic idea. So here are some examples. Probably not extremely new, but gives you a feel. So you have data from images from 4,000 persons. So one way to approach this is to have one output for each person. So you can classify 4,000 persons, and then in the same manner we just discussed, if you get new persons to classify, you just add additional output nodes and use the existing pre-trained neural network for the first layers. So the next to last layer is used as a representation for any face image, also for faces and persons not in the training data. So one way to use this for new persons, a new face, is to calculate the distance between a new face and labeled faces from your Facebook friends based on the representations in the next to last layer. So use this as a distance trick to calculate distance between face images. In often representation learning, the term is used to train like low-level features of entities or time instances. Here, the representation is really close to the output. So much effort is spent in the input layers to normalize the facial images in this particular application. So maybe look at the picture in a second. So C is a convolution layer, M is a max pooling layer, and the subsequent layer L4, 5, 6 are locally connected like a convolution layer. They apply a filter bank, but every location in the feature map learns a different set of filters. So we will learn about convolutional layers in a second. So here's the relatively involved preprocessing to normalize the image, that you don't have to classify an image you're looking from the side. but you normalize it that you look from the front. And then you have convolution layers, max pooling layers, convolution layer, and then fully connected or locally connected layers. Then at the end, really, you have a representation of this image, and then you learn the output labels. And so, and maybe all this processing here is kept static, and then you only, for new phase, you only have to learn the last layer of connection weights here. So speech recognition was one of the first applications of deep learning. So the standard way is to use a hidden Markov model for the experts, so I don't want to explain a hidden Markov model now. But this is replaced by a neural network. No, initially they still used a hidden Markov model, then later they replaced it maybe by deep learning or recurrent neural networks, but initially they kept with the hidden Markov model, but they retrained this probability of the state given the frame, whereas the hidden Markov model typically was using the opposite, the probability of the frame given the state. So the neural network had 4 to 10 layers, 1,000 to 3,000 nodes per layer, no pre-training. They used the rectified linear activation, fully connectivity between layers, and they had softmax outputs. And the features were 25 milliseconds video of audio extracted every 10 milliseconds, and the log energy of the 40 mils scale filter bank stacked for 10 to 30 frames. The training time was 2 to 3 weeks using GPUs, so that was 2013. And then there are two versions. So the interesting story is that they really replaced alternative approaches in speech recognition in the smartphones extremely quickly, and everybody is using them very quickly. I'm not sure exactly how it's done these days, but in general, if you're online, you're using the server solution of the pre-trained of the neural networks, and a much smaller neural network you use it offline when you're not connected. Some advantages people discovered: it's speaker independent. There was always a problem before. You needed a training phase where the recognition system got used to your special voice and your way of speaking, and neural network solutions were speaker independent, so you don't need this training phase anymore. Okay, so here's how the input looks like. This is time, and these are sort of spectral features for different time frames, and these are then used for in the hidden Markov model, which is then the language model to perform the task. And the hidden Markov model, which is not shown here, is nowadays probably replaced by a recurrent neural network. So here different data sets. Here's you see the hours of training. So it's a while ago, so it's maybe not the most up-to-date numbers. And this is the performance or the error of the deep neural network with an HMM combination, and large numbers are good. This is the Gaussian mixture models and HMMs. This is what was used before, and you see that the performance is worse than. So typically they say it's 30% better, maybe on some numbers here. And this is if you have more data to train your Gaussian mixture model. So you improve performance, but you don't get the performance of the deep net and HMM. And these are probably numbers from 2013 or so. So the perspective or aspect number 8 was the convolutional neural networks. They're called CNNs, or sometimes they're called ConvNets. And so initially, so this idea is quite old. So it was developed around 1990. But the full power of this idea has been only realized in recent years. So here, this is a typical data set, and these might be digits written on a letter, part of the zip code, part of the Postleitzahlen, and these are then digitized and normalized, so they can be presented to a classifier. And these are pretty nice written digits, so you can typically have no problems understanding them. So maybe this is not clear that this is a 9, but then people have different ways of writing digits, so it is a challenge. And this is now a demonstration how convolutional neural networks work. So this is too small to be really useful, but it's a good illustration. So we are starting with a 16 by 16 gray-valued picture. So these guys here, they are not black and white, they also have gray levels. And here in this example, we only have 320 training images and 160 test images. And then there are different generations of these net approaches. So the first version has no hidden layer. So it corresponds to 10 perceptrons, one for each digit. And net 1, so this is pre-1990 or something. Net 2 is one hidden layer with 12 nodes and fully connected, so I would call it a normal multi-layer perceptron from the 90s. So this is supposed to be the input image, so here would be a 2 or something. So you see the 2 coordinates. And then the whole image is connected to one layer of 10 neurons. That's what this is supposed to mean. And you learn these connection weights over here. So in effect, you don't really consider this to be an image, you consider this to be a vector of 16 by 16 numbers. And the same for multi-layer perceptron. So here you have the image 16 by 16. Here you have the hidden layer of 12 neurons, and here you have the 10 output neurons. So one output for each digit from 0 to 9. And then, so the goal is to explore more that this is really coming from an image, and also to reduce the number of free parameters, the number of degrees of freedom. So in net 3, we have 2 hidden layers with local connectivity. So it's not every neuron is connected to every neuron. So each of the 8 by 8 neurons in the first hidden layer are connected to 3 by 3 input neurons from a receptive field. In the second hidden layer, each of the 4 by 4 neurons is connected to 5 by 5 neurons in the first hidden layer, and net 3 has less than 50% of the weights of net 2, but more neurons. Yeah, so that's important. It has okay, we will see this in a second. So this is the architecture. So this is the input image again, and now each neuron in the next layer only looks at a small batch in the input layer, so 3 by 3. And then, so in this layer, which is 8 by 8, we of course have many neurons. So each neuron here looks at a slightly a different input patch, so it's sort of shifted, and this is shifted. And there's a reduction, so 3 by 3 moves to 1. But these weights are still unconstrained, so they can be anything. And the idea is a little bit motivated by the way vision works in the brain, that in the first layers in the processing of your brain, a neuron has a very local receptive field, it's called, so it looks at a small batch. But since one neuron, each neuron here is responsible for another batch, we look at the whole image. But every neuron only has a small thing. Before, every neuron was connected to all the inputs. And we repeat the same idea from this layer to this layer, so there are 2 hidden layers now. Again, we have a receptive field here, and each neuron in this layer is responsible for a particular receptive field. And then in the last layer, everything is fully connected, and we have the 10 output neurons again. And so we have more neurons. Obviously, we have 2 layers of neurons, but we have fewer connections because they're not connected to all the neurons in the preceding layer. The next idea which was proposed was weight sharing. So we have 2 hidden layers with local connectivity and weight sharing. So all receptive fields in the 8 by 8 block have the same weights, and the same is true for all neurons in the right block. And the 4 by 4 block in the second hidden layer as before. So this looks like this now. So we have more neurons, even as before. And we have local connectivity, but all the neurons which go from here to this block of neurons, they share the same weights, so they're not free to adapt their own weight vector. All of them have to use the same input weight vector. And the same is here on the right side, so they all, again, use the same weight vector, different from the left one, but shared among all the neurons in this layer. So you have more neurons, but fewer free parameters because a lot of parameters are shared. And in mono deep learning, we have a lot of these layers. And then here we have local receptive fields, and here you have a fully connected layer again. And in net 5, it goes one step further. We have 2 layers of locally connected weights with shared parameters. So this is the whole process is repeated here, and then an output layer of 10 neurons as before. And so this implies some sort of constraints on the way the neural networks perform analysis of the input batch or input images. And we're having more processing units, more units, but not more parameters. And this even more captures the early visual processing in the brain, that sort of there is local processing, but the filters which are applied are applied everywhere in the images, and then there are several filters. So in this case 2, but there might be more. So now I'm showing you learning curves. So one training epoch is one pass through all the data, as we discussed before. The following figure shows the performance on the test set. And net 1, we see overfitting with increasing epochs. And net 5 shows best results without overfitting. So we can look at this figure. So this is how long we are training. And net 1 was training quite fast. But then the performance became worse because we're doing this overfitting. The training error goes down, of course, or the training performance goes up, but the training performance. So this is the training performance, not the error. So up is good, so 100 is good, 0 is bad. So it learns quite quickly, but then overfits in this simple network without even a hidden layer. Then Net2, which was the standard multi-layer perceptron, also had a good learning increase here, and then it didn't really overfit. Then Net3, which had local connectivity, was maybe a little bit better. And then by doing this sharing of weights in the convolutional neural network, you get really a boost in performance. And if you use two of these convolutional layers, the performance is even worse and better and stable, and you don't see overfitting. So this shows you, illustrates you a little bit that this idea of convolutional layers in deep neural networks is really useful, and it allows you to train complex or large neural networks with a lot of units, but avoiding overfitting and getting the benefit of sharing of parameters. So here's the statistics on the performance. So Net5 has best performance. The number of free parameters is 1060, is much smaller than the total number of parameters, 5000. So this is the number of free parameters, and because of weight sharing, you can say we have 5000 parameters. And so here's the statistics. So Net1, so the single layer, no hidden layer architecture, has 2500 links, 2500 weights, and the same number, 80% correctness, probably at the best level. Then Net2 with two layer neural networks has more links, 3200, also more weights, because they are all independent, 3200, and gets better performance. Then Net3 with a local connectivity has fewer links and fewer weights, because we reduce the number of weights, and have 80%, 88%, so more or less the same as the two-layer neural network. Then the constrained neural network, so the convolutional neural network, has 2200 links, but only 1100 free parameters, gets 94% performance, and the constrained neural network 2, which has two convolutional layers, has more links but fewer free parameters, so 5000 links but only 1000 free parameters, and gets the best performance. And nowadays they're getting to, on the real data set and real problems, 99%, better than 99% performance. Yeah, sometimes this is called le net, because it was an invention by Yann LeCun, the person I mentioned before. I showed the picture. In some networks, the deeper layers show interesting features they are deriving. So this is face recognition. The first layer sort of shows these simple feature detectors you also see in early vision systems. Then you see more complex features, and then in layer 3 it even forms some sort of rudimentary image or face templates. So I don't know why this is under construction, but so there are a lot of, or a few parameters you have to consider in convolutional neural networks. So the input might consider of R in layers of size h in 1 times h in 2. And then the output might consist of R out layers of size h1 out times h2 out. That implies that one has R out filter kernels. Each filter kernel is a tensor of dimension or size h1 times h2 times R. And the strides, so-called strides, are h1 in divided by h1 out, and h2 in divided by h2 out. Often the stride is 1, by using a larger stride, I can downsample the image. So this means, do you shift, so you have a kernel size and then you shift it through your image, and do you shift it pixel by pixel or do you jump several pixels? And on the corners, on the outside of the image, you might have to add zeros so the filter doesn't run out of inputs. So this input volume is 32 by 3. So 3 means there are 3 representations of different filters in the previous layer. We imagine 2 borders of zeros around the volume. This gives us a 36 by 36 by 3 volume because we're adding these 2 zero paddings here. Then we apply a conv layer with our 3 5 by 5 by 3 filters and a stride of 1. So stride of 1 means we are shifting always by 1 pixel. And then we will produce a 32 by 32 by 3 output volume. And so they're talking about volumes because for each filter kernel you produce sort of a separate layer of outputs, and then the next layers can work with these representations. But you can also adapt this to sentence classification, so it's not just applicable to images, but also to text analysis. So here's a very simple example. And here you see the power of representation learning. So every word here has a pre-trained embedding, and these are made available. You can download those pre-trained embeddings because people make them available. So the mapping from word to embedding, which is a vector of a certain size, maybe a couple hundred real numbers. So each word is mapped to a separate latent embedding vector, which comes from a dictionary. And then you have a deep convolutional neural network, often pre-trained, and then maybe you classify the sentiment in the class. Is it positive, negative, aggressive, whatever? And this is shows you a little bit that this idea of convolutional neural networks and weight sharing can also be applied not just to images but also to text. Again, here, besides the mapping from words to embedding, you don't need any feature engineering, which used to be extremely important in natural language processing, and now often it's replaced by deep neural networks. Yeah, pooling is a little bit a strange operation. So essentially it's a way of reducing complexity. Maybe I show the image first. So for example here you take a batch and simply work with the average or the maximum activation in this batch. So it's in a form, it's a subsampling, downsampling operation. So for example, one could compute the mean or max value of a particular feature over a region of the input space. So feature means output of the previous layer. The summary statistics are much lower in dimension compared to using all the extracted features, and can also improve results because it also reduces overfitting because you have reduced the number of dimensions. And this operation, this averaging or this type of calculation is called pooling. And people use mean pooling where they calculate the average over a certain size of pixels of neurons, or max pooling where they calculate the maximum activity of the neurons under consideration. Yeah, it's useful in vision because it reduces the computational complexity because you're downsampling essentially, and it provides some form of translational invariance. So the exact position of an edge within the pooling window might not matter as long as the edge detector says there's something interesting in this region. And since it provides additional robustness to position, max pooling is thus a smart way of reducing the dimensionality of intermediate representations. Mean pooling is related to a convolution layer with a rectangular or uniform kernel and a large stride. Yeah, because in convolution, so you can think of it as a very simple convolution layer, just taking the mean over so a very specific filter, mean filter. The max filter cannot be implemented as a simple convolution. Also, I want to give you a little bit impression how these deep learning neural networks look like. So this shows AlexNet, which was in fact the architecture which was giving this amazing results. I think it was 2011, which then convinced everybody to that neural networks or deep neural networks have something really special because they were better than on data sets, on images which experts in vision research have tried their best methods on. And even I think in the first attempt it was already reducing the error by 30% or so. And the first one, this was called AlexNet because the main author was first name was Alexander. Alternatives are Inception or VGG, Visual Geometric Group from Oxford. So here you see the image here on the left side. You see that they're applying max pooling, applying convolutional layers. So they get here a lot of different filter dimensions. So that's why it's typically image is 2-dimensional, but if you also include all the different kernels you're using, it becomes a 3-dimensional thing. So here you have the different filter kernels and max pooling, convolutional, fully connected, dense, fully connected layers. And here you have 1,000 classes. So the task was to decide if on an image was a cat, a dog, or something else. 1,000 different object classes. So it was published in 2012. So it had 7 hidden units, 7 hidden layers, 650,000 units, 60,000 parameters. It used on the order of 1 million images, and somebody hand-labeled them. It was a group from Stanford. It used GPU implementation with a 50 times speed up over CPUs, and at that time I trained for a week. The ResNets are sort of going to some extreme. So the original ResNet had 152 layers and became world champion in the ImageNet database competition. Here's some examples which are popular now: AlexNet, VGG networks, GoogleNet, which is an Inception network, and many variants. So the idea is sort of to always learn the difference in error, what the previous layer was doing. So because there's 2 layers which calculate something, but they only have to learn the difference to what has already been learned, and then you stack this idea and you get up to 152 layers. So that's so ResNet, from a residual network, it has to learn the residual. So it tries to focus on the things the previous layer could not learn. There's something called regional CNN or RCNN. There are different variants: fast RCNN, faster RCNN, mass RCNN. And the task here is to find objects. So in the first application of AlexNet and so on, there was only one object in the image which was important, and the image was supposed to be classified for this one image. But most images, of course, consider many objects, and the task is to find these so-called bounding boxes, which are surrounding the different objects. So you see them here very nicely. This is a person. This is a bounding box for the horse, for the dog, for the car, for the person. And this is a family of RCNN approaches which are able to do exactly that. An aspect which has been in discussion in recent years, and maybe even today, are these adversarial examples. And the fact is that deep, high-performing neural networks can be fooled by examples intentionally constructed by using an optimization procedure to search for an input that is very close to a real data point, but produces a very different label. So here's one example, but there are many more. This original image, and it was correctly classified as a temple, and then people added a little perturbation, and then they produced an image which was, for us it looks the same, but the deep neural network classified this as an adversarial example, as an ostrich, and this is considered a problem if you have safety critical applications. But one thing to know is that this perturbation was calculated deterministically, so it's not a random perturbation. It was calculated to be able to disturb the classifier in an optimal way. So this is not happening in the real world, at least not typically, but it's sort of strange that we don't see a difference. For us, these two images look the same, but the classifier thinks they are very different objects. And one good explanation is probably this manifold concept we have already discussed and will discuss more in next lectures. So if the data was generated on a manifold, so now the input data was not all everywhere in input space, but maybe on a sub space or submanifold, then the performance might be extremely well if the test data is also on the manifold. But if the test data is not on the manifold, the deep neural network might do pretty unexpected things. But it's an active research, and people are trying to develop smart ways of avoiding this problem by training the deep neural network in a way that it doesn't show this, is not very sensitive to this effect. So where from here? So there will never be enough labeled data to learn it all. In particular, if you have to start from scratch, and people argue the Google Cat recognizes sees more cat images than any child, but it's not as good as a child. One idea people are pursuing is unsupervised learning, that you first learn the statistics of the world, and then training a classifier on that might be easier. So there are still sometimes news articles that Lecan, Benjo, and Hinton say unsupervised learning would be the solution to everything. Or Lecan advertises something called self-supervised learning, which works like in a time series type of problem where you make a prediction about what happens next, and then you get an actual measurement, and you don't even need some person labeling the data in these type of applications. But this is ongoing. It's an ongoing discussion. There are a lot of tools available. I think PyTorch is currently very popular. It's a Python library for machine learning. You have to map it to GPUs. CUDA is the language to use there. Theano used to be very popular, not so much. Most people use PyTorch. Um, some approaches are more high level, like Keras, where I mean, it's always also a question, do you want to use standard approaches, then you can use a high level interface, or do you want to manipulate a lot in your architecture, then you have to be at a deeper level, but then also you need more expertise. TensorFlow is the framework developed by Google, and they also develop special chips, TPUs, which use low energy and are very good at performing some of the necessary operations. And they can also be implemented with low energy after training. So there are a number of things. So these are some early successes. Microsoft Speech, who demonstrated deep learning which converts spoken English into computer-generated Chinese language. So this translation from English to Chinese. And Android speech recognition from Google. And many improvements on the speech recognition and also on the translation systems. Yeah, so they used to made this Google announced this Google neural machine translation system. So this is ongoing neural machine translation. Facebook uses a lot of face recognition if you permit it to use, which is working surprisingly well. Yeah, AlexNet, we discussed already, was one of the first networks which were so successful in image analysis. It was the first one. ResNet was 2015. GANs, which we'll discuss later, which can do this amazing image transformations. Then AlphaGo was 2015, AlphaZero 2017 in board games. AutoML is a current trend that you make deep learning very easy to use, and also in a way that the user doesn't need to apply all these has to be very knowledgeable. Everything is tuned automatically. The architecture is selected automatically. Yeah, self-driving cars is one of the cool applications where deep learning is being applied. So finally, we want to talk a little bit about why deep learning might work so well. And a number of different theories are being developed. We discuss a little bit one of them from Tommaso Porcio, who addresses approximation theory, optimization, and learning theory. Yeah, there's a YouTube you can find online, or here's a paper you can download. So essentially, we are addressing a case what we called 1C, which is the compositional case. And the question is, when and why are deep networks better than shallow networks? So the question is, given a function out of a target function class, what is the best fit a deep neural network can obtain? If we cannot make any particular assumption about the function class, so maybe just some general smoothness assumption, then, as we discussed before, we are in case 1 with the curse of dimensionality, and we get this really bad scaling behavior, that the number of hidden units or the number of basis functions scales epsilon, which is the error you're willing to tolerate, to the power of m. M is the number of inputs, m is the smoothness parameter, and this really grows exponentially with m. So the more inputs you have, the worse the problem gets. And as we did with the analysis in neural networks, we have to not assume that the functions are generated uh, just by constraining the smoothness of the functions, but that the functions have a certain compositional structure. So essentially, nature generates also functions which are functions of functions of functions. So below here, there's an example. So you have h functions, different h functions which are then the input to another h function, which are then the input to another h function, and this calculates a function of many inputs, but these functions only depend on two inputs, and then there's a hierarchy of combining this in a tree. So this would be a flat architecture. Everything is connected to one output, and here you have this compositional structure. And a flat neural network would still have this bad behavior, as we discussed before. But if you use a deep neural network for this type of target functions, then the order, the number of hidden units or number of parameters is on the order of m divided, so that's the number of inputs, divided by m square, which again is a smoothness parameter. So the smoother, the fewer parameters you use, and then 1 divided by epsilon square. So this formula is pretty amazing because there's only 1 over epsilon square, no bad scaling behavior in terms of the accuracy you're trying to achieve. M, the number of inputs, appears in this formula, but it appears in a linear term. And linear terms are not really dangerous. And if you have a very smooth function, then this is even reduced further. And you can find this formula in this paper here. So it looks like that deep neural networks are suited for these type of compositional functions, which seem to be the ones which actually occur or are generated by nature in many applications. And these functions have this compositional structure, and also neural networks, of course, have a similar hierarchical structure, so there's a nice match. So essentially the secret is that deep neural networks seem to capture some of the regularities which occur in actual images in the real world. So this was the issue of approximation theory. Then there's the question of optimization and the question of local optima. So as I discussed before, excuse me, deep neural networks don't seem to suffer from local optima. And one property people try to explain this issue with is that there are so many free parameters, and so MP is so our number of free parameters is much larger than n, the number of training data, and then the cost functions are sort of degenerate and that and take on more volume in parameter space. So maybe this picture is telling you. So this is sort of a degenerate cost function. So anywhere you move in this direction, the cost doesn't really change. So although it looks like a two-dimensional problem, it's really in a way a one-dimensional problem. And supposedly this takes up also a lot of volume in this view. So the algorithm has a very good chance to find this degenerate optimum because it's difficult to not go through this. This is sort of the intuitive argument, this degeneracy that you have more parameters than data points means that there's not a clear optimum, and these non-clear or degenerate optima are easier to find. And this is definitely confirmed empirically that overparameterized CNNs don't have a major problem with local optima. So maybe this is another blessing of dimensionality. So if you make your neural network too large, the problems of local optima sort of disappear to some degree. So Poggio says over-parameterized deep networks have many global minimizers that are generically degenerate. Other critical points of the gradients are generally isolated. So they are there, but they might be very difficult to find or trap into by stochastic gradient descent. Finds with very high probability large volume zero minimizers. So this is even the case where, because if you have more data points, fewer data points and parameters, you can get zero error. And SCG behaves in a similar way. So now here, that's why the error is zero, because if you have enough parameters, you can always get zero error. So that seems to be a reasonable explanation in my understanding why deep neural networks optimize well. They find good optima and don't seem to suffer from bad local optima. Then the third question, so the first one was approximation, the second one was optimization, the third one is the statistical error. So we have so many parameters, don't they sort of introduce a lot of uncertainty? And then the question is, how many data points do we need? So the idea is that, for example, if you look at this example, there's only one really important parameter, and that's this one, and this one is not so important because obviously the network doesn't really consider, it doesn't change the cost function if you move in this direction. So this means that, or the interpretation is that there's something like an effective number of parameters, MF, which is much smaller than the number of parameters in the model, and maybe this M effective parameter is really relevant for calculating the test set error based on the statistical error, not on the approximation of error, but on the uncertainty in the parameters. Because typically these terms have this term number of parameters divided by a number of data points, and if you can reduce this MP by NF, so instead of using the number of parameters, you use the number of effective parameters, then this error introduced by the uncertainty in the parameters can become much smaller. So the overparameterization doesn't hurt necessarily in generalization performance as long as the number of effective parameters stays small. And Poggio also gives an estimate that the number of shallow networks increases exponentially, whereas if you divide by the number of required parameters in the deep networks. This is the estimate of the number of parameters you have to use. So for deep ones, use much lower number of training parameters. So Poggio says the much used variance of SGD, of stochastic gradient descent, maybe with batch normalization and weight normalization, perform minimization with unit norm constraint, which is equivalent to maximizing margin under norm constraints. So this is a technical formulation of what I've just said, that the number of effective parameters is important, and that might be much smaller than the number of actual parameters. That's, in a way, the deep neural network is automatically regularized. So why is this lecture on machine learning, not deep learning? So if you only know deep learning, you're pretty shallow. So there's a little bit temptation that you get so much involved in the tools and the training and the successes, and um, maybe it's might be good enough for your application or for forming a startup company, and then maybe you learn about the newest tricks and always try them out. Um, but then you're missing an understanding of what's really going on, and that's what I'm trying to say here. I think it's um, yeah depends of course of what your goals are, but uh, deep learning gives you a lot of interesting tricks and maybe some understanding by the work, but it doesn't give you maybe often a very deep understanding. So it's deep learning without deep understanding. And that's why I think machine learning gives you a wider perspective on learning. And and of course, there is another lecture on deep learning. So if you're completely only 100% interested in deep learning, you can go to the other lecture, which will be taught probably in the winter semester. And yeah, I'm trying to cover some of the major ideas in deep learning because they're really interesting and also help you understand other methods or other models quite well, and also simply because they are in many ways the best performing approaches. Um, I mean, in my team, we are not trying to derive the best deep learning model for, let's say, image classification, but we are more interested in using deep learning as an integral part of more complex solutions, and they work very well, and we're very happy with them. But typically, it's not just a deep learning neural network and other in our worlds and our applications that really solve the whole problem just by themselves. Okay, thank you very much for your attention, and I see you next time.